Hi, and welcome back to the Implementing and Administering Cisco Solutions, the CCNA 200-301 video series course by EC Council. My name is Glenn Singh. In this video, we'll be taking a look at understanding IP version 4 or IPv4, and we'll be finishing up this video by understanding subnetting and VLSM. So let us dive on in. Every device on a network contains an IPv4 address or an IPv6 address. So we can think of an IP address to be like your street address together with your house number. So therefore, if you need to give, let's say, the pizza driver some directions, you can give him the community address, the name of the street you're living on, and your house number, so he can use all this information to quickly find you and to deliver the pizza to the right place. With an IPv4 address, it is made up of 32 bits, and these 32 bits are in the form of binary notation. Simply that computers are able to read binary or ones and zeros to put simply. However, as humans, we are able to read decimal values. So we might see an IP address that looks something like this, 192.168.1.2. Each of these values here, for example, the 192 is what we call an octet, and we use periods or we use a dot to separate each octet. So therefore, an octet is made up of 8 bits in length, and each 8-bit is separated by a dot, as you can see here. Beginning your journey in network engineering, it's very important that you understand how to convert binary into decimal and vice versa. We as humans, it is quite easy for us to understand the decimal, but computers need to be able to understand the binary notation. And we need this information because there may be instances where, let's say, a PC is not able to communicate with another device on a network. And as an upcoming network engineer, it's very important that we be able to actually identify the source of the problem, especially if we happen to, let's say, assign the incorrect IP address. So now, let's do a simple exercise to actually convert a binary number to a decimal. To help you with this conversion, I have designed an Excel sheet to help you doing the conversion between binary to decimal and vice versa. To find this Excel sheet, you can head over to my GitHub, like so. The URL is github.com/GlennDSingh, and ensure you visit the code-red-CCNA-200-301 sub-URL. Once you reach there, you will see Domain 1. Click on Domain 1 Network Fundamentals, and you will have this Excel sheet, which is named Binary Decimal Conversion. Simply download the Excel sheet and open it with Microsoft Excel. Once you open the Excel sheet, it will look like this. So let us start by discussing how are we going to start with our conversion. Well, the first thing we want to learn about is converting binary to decimal. The key thing to always remember is in the world of networking, whenever you are making a conversion, let's say binary to decimal or decimal to binary, only convert one octet at a time. So let's imagine we have a random number. Now, this random number must be up to 8 bits in length. So let's say we have a random number of 1010101. So this is 1, 2, 3, 4, 5, 6, 7. And let's add one more value here. So we get a total of 8 bits. Now, the thing about binary is in base 2. And this means that each of these bits is actually assigned to a power of 2. So for example, this bit across here is actually assigned to 2 to the power 0, while this one 2 to the power 1, this value here 2 to the power 2, this one 2 to the 3, 2 to the 4, 2 to the 5, 2 to the power 6, and this bit across here, 2 to the power 7. Now what I have done is actually written out the powers of 2 in this table here. And I have written out the actual decimal value. So to put simply, 2 to the power 0 is actually 1. 2 to the power 1 is 2. 2 to the power 2 is actually 4. So you're probably wondering, how did we get this 4 here? Well, 2 to the power 2 is actually 2 multiplied by 2, which is equal 4. So what about this one, 2 to the power 3? Well, that means 2 to the power 3 is equal to 2 multiplied by 2 multiplied by 2, which is equal to 2 2s are 4, 4 2s 8. And as you can see, we have up to 2 to the power 7. So what we can do next is simply assign these values here, the actual number, into this table. So we'll get 1 0 1 0 1 0 1 1. And whenever we see a 1, it means that the power 2 is actually on. So which means that we will get 128 here. This will be 0. This value will be 32. This value here will be 16. Actually, not 16. It will be 0 because this here is 2 to the power 4. But the actual binary number here is 0. So this means it is off. So 0. Since this is 1, we'll burn down this 8. This value is 0. This value here is 2. And this value here is 1. So give me a second. And what I will do is simply show you how this calculation is made. But to put simply, all we need to do is add up these values, which is 128 plus 32 plus 8 plus 2 plus 1. So let me clear up the board and I'll show you how the actual Excel sheet works for us. So as you have seen, the table actually made the calculations for us. However, it's very important that you are able to add these values on your own, because during the CCNA exam, you will not be able to use a calculator or even a mobile phone or even the calculator on your desktop to make these calculations. So it's really important that you remember this table and the associated values. So notice here that we could take any number that contains 8 bits and simply insert it in the table, and you can actually make the calculations manually, which is 128 plus 32 plus 8 plus 2 plus 1, which will give you 171. So how about we take another number? What if all these bits are all ones? What is the total value we can have in an octet? Well, let's try that out. So as you can see, if all the bits are ones in an octet, the maximum value will be 255. So therefore, any octet that is greater than 255, it is not a valid IP address. So to put simply, an octet can only range between 0 to 255, nothing greater. And this is why that whenever we make our conversions, we only convert 1 octet at a time and only 8 bits at a time. So now that you have an idea on how to convert binary to decimal, let's take a look at doing the reverse action, converting decimal to binary. So I'm pretty sure you remember the table. Well, we are going to reuse the information from the table before to help us make our conversions in 8 simple steps. Again, on the Excel sheet, simply open it, and this second tab at the bottom here, which is called decimal to binary, simply click it, and now we have a table to work with. So how are we going to use this table? Well, definitely, we can only convert any number between 0 to 255, nothing greater. So what can we do? Well, let's take a look at actually converting, let's say, a random number, and I will explain the process for you. So let's say that we want to convert, let's say, an odd number like 175. Well, what we can do is simply insert the value in this box here, and then we can see the working that is actually taken place on the left hand side. So let's actually do that. So simply click in the box and insert any number between 0 to 255, and you will see the calculations taking place on the left side. So let us type 175 and let's click outside. So to give you a full breakdown of what happens, because you need to know this as well as an upcoming engineer, is we are going to start with a number which is 175, and we are going to attempt to subtract the highest power of 2, which is 2 to the power 7, which will equate to 128. So we ask ourselves, can we subtract 128 from 175? If the answer is yes, we place a 1 and we work the calculation down here, which will give us 47. So remember, we already use this power of 2, which is 2 to the 7. So the next value is 2 to the 6. So now we insert 2 to the power 6, which is 64 down here. So now we ask the question, could we take 64 from 47? And we can't. So we put the answer 0 to indicate no, we cannot. What we will do now is simply take this 47, bring it down here. And now we'll move to the other power of 2, which is 2 to the power 5, which is 32. So now we ask the question once more. Could we take 32 from 47? And the answer is yes. So we place a 1 and we work out the calculation, which is 15. Now we put the other power of 2, which is 2 to the power 4, which is equal 16. We ask the question once more, could 16 be taken away from 15? And the answer is no. Therefore, we bring the 15 down here and we move on to the other power of 2. Which is 8. 2 to the power 3 is equal 8. We ask the question, could 8 be taken away from 15? The answer is yes. We place a 1, we work it out, we get the remainder of 7. So now we move on to the other power of 2, which is 2 to the power 2, which is equal 4. Could 4 be taken away from 7? Yes. We place a 1. We work out the value, as in the remainder, we get 3. We move on to the other power of 2, which is 2 to the power of 1. Could 2 be taken away from 3? Well, yes. So we place a 1, we work out our remainder, which is 1. We move on to the last power of 2, which is 2 to the power of 0, which is equal 1. So could 1 be taken out from 1? Yes, and we place a 0. And what we do is we take the values from top to bottom and place them in order across here. So therefore 175 is equal 10101111. So please do take the time to perform different calculations, but remember the values can only be between 0 to 255. Any value greater than 255 is not a valid IP address. When it comes to IPv4 addresses, there are two main IPv4 address spaces. These are known as a public address space and a private address space. The primary difference between both of these address spaces is that the public IPv4 address space is routable on the internet. What this means is any device which requires communication with another device on the internet will need to be assigned a public IPv4 address on its public facing interface. This interface is connected to the internet. So now let's take a look at the public IPv4 address classes. Typically, we use only the first three classes, Class A, Class B, Class C. And as you can see, we have the ranges of each of these address classes. Class D is used for multicast, which is for very special programs and applications. Class E is for experimental use and reservation. However, if you visit a site, let's say you go to perform a speed test, you simply need to look at the first octet, or let's say the first 2 octets of your public address, and you can determine whether you have a Class A, Class B, or Class C public address. Please keep in mind that these class ranges are very important to know for the exam. Additionally, if we use, let's say we use the entire public IPv4 Class A, B, and C to assign these addresses to all devices on the internet, and let's say all devices within an organization, definitely will eventually, or we would have run out of IPv4 public addresses perhaps decades ago. So, the organization which created the whole IP address scheme for us is called IANA, which stands for the Internet Assigned Numbers Authority. They created both a public and a private scheme. So, what they determined is they created a private IPv4 space. And this private IPv4 space is defined by RFC 1918. So to put simply, there are 3 classes of private IPv4 addresses which are located for private use only. What this means is a private network such as, let's say, your home network, your organization network, or any sort of private local area network, these addresses can be assigned on it. So I could be using a particular private class of private IPv4 address on my network. You could be using the same and there will be no conflict, simply because private IPv4 addresses are non-routable on the internet. So therefore it will never work on the internet. With private IPv4 addresses, they can be used within organizations and private networks as mentioned. However, on the internet, only public IPv4 addresses are allowed. And the thing about the internet is each device on the internet requires a unique public IPv4 address. This means if a device is connected to the internet with a private IPv4 address, there will be absolutely no network connectivity to devices that are actually on the internet. Most ISPs or most internet service providers usually implement a security filter to prevent any sort of private IPv4 addresses from actually entering their network. Similarly to the public space, we have the private space, which is made up of 3 address classes: Class A, Class B, and Class C. Notice that the Class A is made up of the entire 10 network. Class B ranges from 172.16.0.0 to 172.31.255.255. And Class C is everything within the 192.168 network, which is what we are very common with or very familiar with. For each class of address, we have an accompanying subnet mask. So what exactly is a subnet mask? Well, the subnet mask is used to identify the network portion and the host portion of the IP address. So to put simply, the network portion is like your community address. Everyone within your community has your same community address, but the host portion is like your house number, which makes your entire address unique. So the subnet mask is simply used to determine the number of available IP addresses on a network as well. So apart from helping you identify, let's say, network and host portion, you can also be able to determine the number of available IP addresses on an actual network or a subnetwork. So what if 2 or more devices, such as let's say computers, are communicating over multiple networks? the subnet mask of each device simply determines if a computer should send a packet to a default gateway or not. So let's take a look at the default subnet masks. These here are the default subnet masks. We have Class A, which is 255.0.0.0, Class B, 255.255.0.0, and Class C, 255.255.255.0. And these here are the default subnet masks for each of the address classes A, B, and C. Each IPv4 address has their own default subnet mask. So an IP address such as 10.10.10.1, which belongs to the private Class A address, will use a Class A subnet mask of 255.0.0.0. Another example is, let's take a look at this IP address, which is 192.5.4.6. Well, looking at the first two octets, or just the first octet, we can determine that this here is a public Class B address. Therefore, it will have a default subnet mask of 255.255.0.0. However, there may be instances where a custom subnet mask may be used, but we'll take a look at a custom subnet mask when we dive further into subnetting. A very important key terminology to remember is, what is the network prefix? Well, I'm pretty sure, perhaps by reading a book or doing some research online, you'll notice that after an IP address, you will see a slash with some numbers that look similar to this. So, for example, let's imagine you have a IP address of 192.168.10.16, and then you'd see /24. So what does this slash means? Well, this slash with a number is simply what we call the network prefix. And this here is a shorthand way of representing the entire subnet mask. So you're probably wondering, how exactly can we use, let's say, /24 to represent, let's say, the actual subnet mask, which is 255.255.255.0. So let's take a look at how we determine this. So what we can do is, let's say we have a Class A address of 10.10.10.1/8. Well, let's take a look at the default subnet mask for a Class A address, which is 255.0.0.0. We can simply convert this decimal into binary, and then we'll get 8 ones for the first octet, and each of the remaining octet we have 8 zeros, 8 zeros, and 8 zeros. But notice carefully how many ones are there in the subnet mask. There are 8 ones. So therefore, we can simply use /8 to represent that there are 8 ones in the subnet mask. So therefore, if you write the full version of this network prefix into binary, you will get this value here. And converting it back to decimal, you'll get the default subnet mask for a Class A address, which is 255.0.0.0. Another key important thing to understand in networking is we need to be able to identify the network ID of a host device. And to help us to identify the network ID, the subnet mask actually plays a very important role. So to put simply, the subnet mask helps determine which network or subnet an IP address belongs to, an IP address being a host machine. So the process to determine the network or the subnet is done by a process called ANDing. So what we'll be doing is ANDing the IP address and the subnet mask together, and the result will provide us with a network ID. So what are the laws of ANDing? So let's take a look. These here are the laws of ANDing. So 0 and 1, we have 0 as a result. 0 and 0, the result is 0. 1 and 0, we get 0. But 1 and 1, we get 1. So let's take a look at how we can go about determining the network ID properly. So we can use these following steps, and these are my personal steps. So definitely you need to have an IP address and a subnet mask of a host machine. So the first thing you want to do is convert both the IP address and subnet mask into binary. Next, you will add both the IP address and subnet mask. The result will be the network ID, but of course it will be in the form of binary. Simply convert the result back to decimal and you'll actually get the network ID. So let's take a look at the actual possible cause of determining the network ID. Take a look at these two devices. We have PC1 and PC2. Both of these PCs has an IP address and they have a subnet mask. Now, PC1 IP address is 192.168.126. PC2 is 192.168.1.129. Their subnet masks are exactly the same. But there's a problem. PC1 is not able to communicate with PC2 and vice versa. Now, the IP addresses are configured exactly as shown together with a subnet mask. Now, you're probably thinking, is a cable bad? No. What if the cable is working perfectly, all devices are on, and everything is physically connected as how it should be? But we need to determine what is a possible cause for these two devices are not able to communicate properly. So to determine this, let us work out the network ID for PC1 and the network ID for PC2 and compare them. So what I've done, I've converted the IP address of PC1 into binary, and also I have done the same for the subnet mask. So let us actually AND each of these bits in the IP address against the bit within the subnet mask itself. And our result will be, so we know 1 on 1 is 1, 1 on 1 is 1, and of course we have zeros for the rest of this octet. So we have now achieved the network ID for PC1. Let us convert this back to decimal. So converting the network ID back to decimal, we'll get 192.168.1.0. Alright, let us work out the network ID for PC2 and then we'll compare both of them together. Okay, and let us now convert this network ID for PC2 to decimal. We'll get 192.168.1.128. And look at this, two different network IDs. So what does this mean for us? Well, this means that if these two devices, their network IDs do not match, for example, so this means that PC1 is located on the 192.168.1.0 network and PC2 is located on the 192.168.128 network. So therefore, this is evidence that both of these devices, PC1 and PC2, are on two totally different networks. And this is the reason why both of them will not be able to communicate. So this here is actually the end of part 1 of this video. In the next part, we'll be actually starting subnetting. So I hope this video has been informative for you, and I hope to see you in the next one.